Okay, good afternoon. Hello, everyone. My name is Miki Elad, and this is the first meeting in this course on generative AI diffusion models. Please mute yourself, please. So this is the first meeting in this course. What I'm going to do in the coming few minutes is to talk about the administrative issues of the course and a little bit about the content of what we will be covering. And then we will start the material. Our starting point today will be some sort of a mathematical review to introduce some basics in probability theory and introduce the notations, because this is going to be the language that we will be using. More on this comes in a minute. And once we finish with all of this, which means, roughly speaking, the coming hour, we will actually start the material. This would be the second hour today. So let's go on, and you are welcome to stop me anytime with questions, anytime. Just raise your hand or something, and just step in, unmute yourself and step in and talk. And if you are uncomfortable asking in English, you are welcome to do so in Hebrew as well. Okay, so let's proceed. Good. So again, I'll start with administration. This is us. This is the team. Noam Elata is our teaching assistant, TA. I am the lecturer, Miki Elad. We are going to meet here virtually only on Sundays, 4:30 for 2 hours, 2 academic hours, you know. No need to talk about the prerequisites. Those of you who are formally registered know exactly that they are satisfying all the conditions, no problem about it. I remind you that this is a 2 credit point course. Here is the number above. I think you do see my mouse, 236-610. And there is a webpage to this course, and I'll come back to it. So this is the webpage. Don't bother writing it down. You will see a very easy shortcut to get to it. Okay. In this course, we are going to talk about diffusion. So diffusion is a basic concept in sciences. It comes up a lot in chemistry, in physics, in math, in the context of the heat equation, and in image processing. And I should say, this is a course on image processing. And I'll mention this again and again during the coming hour or so. So in image processing, diffusion has a very important meaning. 30 years ago, a new field in image processing suggested to design filtering techniques for images based on partial differential equations. Please don't be alarmed. We are not going there, okay? But this is something that people did a while ago. And it developed a lovely theory. Today we will see a glimpse of it, but just as a matter of background. So diffusion has a lot to do with image processing in the context of filtering, smoothing, while preserving edges, etc. And all this is not relevant to us. The diffusion that I will be referring to is something different. It's a diffusion of probabilities. It's a diffusion where one probability, typically a Gaussian, is warped and changing and breathing over time and changing to become something else. This is the diffusion that leads to a hot topic today in AI, in generative AI, generation and synthesis of images and other material. This is the topic we will be diving into. So we are going to discuss diffusion models. This image, for example, is a product of such a software. In fact, it's coming up from a code by Google called Imagen. So basically give a prompt, a sentence, ask for something, and you get this amazing looking picture synthesized by a piece of software. The same goes for videos, audio, music, even free text can be generated with these breed of algorithms. And this is the topic of this course. However, in this course, I will concentrate only on images. Much of what I'll describe apply to all the other contents, but I will keep talking about images. Why? Because this is my field of interest, and this is the kind of work that I'm doing with my students. I spoke about diffusion of probabilities. This is an illustration of this. What you see here is a random vector, Gaussian distributed, IID, and it is going through a process, iterative process that slowly and gradually turns it into a good-looking image. So here we sample from a well-known distribution. Here we get a sample from the image distribution, which is so complicated. The notion of synthesis or hallucination of images should remind you of other tools that are very commonly used in deep learning in recent years: variational autoencoders, GANs, normalizing flows, energy-based methods, etc. And yes, what we will do here is to suggest the next chapter in this sequence of achievements that took place in the past 10 years. Diffusion models, and I'll mention this again and again during the course, have several interesting benefits. I'm writing here relative simplicity. Yes, it is simple, at least the core of it, but as you will see, the simplicity is not that clear. Let's put this aside. Solid theoretical foundations, definitely. You know, for those of you who are practicing and knowing things in deep learning, much of what we do in deep learning is technical, intuitive-based, empirical. Diffusion is very much different. Diffusion has lovely theory behind the scene. And this is something that I find most appealing. Excellent performance. These are the best generation or synthesis algorithms these days, and they have wide applicability. They can be changed and warped towards all sorts of subtasks, as we will be showing carefully during this course. Again, talking about our staff. So this is me, Miki Elad. I'm a professor of computer science in the Technion, and my fields of interest have always been signal and image processing and machine learning. In the past 2 years, I published a list of papers on diffusion. All of these are papers on diffusion models. As you can see, 2 of these papers are with Noam Elata. So let's turn to Noam Elata. Noam is a PhD student. He's doing his PhD under the supervision of Tomer Michaeli and myself. And he already published 2 papers on these topics of diffusion. So Noam will be very helpful in a lot of directions when you are debating about your project, something I will talk about in a minute. Now, I came to this field of diffusion, I came to this field of diffusion in a very awkward way. I found my interest in this field because of the connection it has to image denoisers. You know, there are bunch of algorithms that can take a noisy image and clean it up and create cleaned image. Over the years, I wrote many papers and did all sorts of research directions on designing such denoisers and taking them to other tasks. And this is exactly what's happening here. And when I saw this, it created the initial interest. Once I started diving in, I found other reasons to be interested in diffusion. One thing that interests me along the years is the solution of inverse problems. You know, you get a corrupted measurement, some corrupted image, and you want to clean it up, clear it up. How do you do that? As I'll show you carefully in this course, diffusion models bring a revolution to this field, change the language entirely and create new opportunities. Here is another reason to be fascinated about diffusion models. Another reason to love diffusion, and I mentioned it, is the mathematical background. It's so solid, so beautiful, and so well structured, very elegant. Question: if there is one reason for this, the creation of this course, is my desire to learn this field. When I want to learn something, I'm actually teaching it, and then I'm investing a lot in learning, and then I'm also learning from you. You will be covering some of the papers that were published in the past year, and we will all learn from each other. And I said this again, and I'll mention it again, while diffusion are general techniques for synthesis of content, we will take these to imaging mostly. In some of your lectures, we will allow exposure to other kind of signals or data that can be generated. And one more thing that I should say is that I'm giving you my subjective point of view. All the slides here are my creation, and you are welcome to argue, to question everything that I tell you. Okay, let's proceed. So let's be clear about this course. This course is the intersection between diffusion models and image processing. This is how I'm going to build this course. And this course is highly mathematical in nature. You will see it happening even today. If this is the general field of machine learning, and if this is the general field of image processing, and there there is an overlap, and the overlap is growing and growing and growing up to the point where image processing becomes a subfield of machine learning. Then in this intersection, much of the overlap is because of deep learning. Within this overlap, diffusion are taking a growing role. And as you can see, diffusion is not just happening in image processing and machine learning, it's happening elsewhere. In fact, diffusion comes from very elegant mathematical theory of stochastic differential equations. It comes from physics, it comes from chemistry, and we will mention some things about this, but again, we will concentrate on the more civilized and simple signal processing kind of things that translates to what we need. Okay, now this is a seminar course. What does it mean? It means that in the first weeks, I'm not sure how many, but it's going to be 6 to 8, the lectures will be given by me. I created a series of lectures in which I'm describing the whole field in a very structured way. And these will be the first lectures. One of those lectures, by the way, will be given by Noam, the one that touches on stochastic differential equations and ordinary differential equations. Then comes your part. Each of you in pairs or in singles will do a project on a paper, and we expect you to present in class your work. How exactly? I'll say something about it in a second. It is very likely, because of the length of this semester, that we will not get the chance to cover all your lectures within the semester. And if this is happening, then we will find a date after the exam period to have another meeting where we go through the remaining lectures, etc. While in the beginning I was planning to check attendance, I'm not going to do that. So you are welcome to come and go. You can just skip those meetings and just look at the videos that I will be sharing with you. So attendance is not mandatory. As for the webpage of the course, this is my webpage. You just write Michael Elad and you find this webpage. Under this page, you can find the link courses. So click on it. And under courses, you take the current courses. And this is it. You click on this website and you end up in our page. In this page, I will share the videos. It's already containing some content, for example, the list of papers that I will mention in a minute, etc. Now, let's talk about your projects. I'm talking about those of you who are formally enlisted to this course. You're supposed to choose a paper. You can work in pairs or singles, not triplets. And you're supposed to choose a paper either within a list of papers that we are providing you or from outside, anything that you find that might be relevant, as long as you approve it with Noam and myself. So you cannot just choose the paper, you have to approve it with Noam and me. And once it is approved, read it carefully, learn it, and prepare a presentation on it. The presentation is about explaining this paper to this class, okay? Just explaining the paper. If it so happens that you found slides relevant to this paper on the web, you are welcome to use them. Don't stop yourself from using them. This is fine with us. Just give the proper credit, and it doesn't take anything from your achievement. Okay, so you give the lecture, but first you give it to me. I want to make sure that the quality is high enough so that it is worthy of being presented in class. And once it is approved by me, you present it in class. In parallel or afterwards, you're expected to do an extension of this paper. You're supposed to take whatever you read, talk with Noam and me, and suggest something that goes beyond what they did. Another experiment, another derivation, another application, something else. Do this, extend your presentation, include more slides about your portion, and then present it again. If you are successful in doing all of this fast enough, then you can give us the presentation with this included. If not, we can have a second round of presentations just to Noam and me. Okay, now, most of you will have to run code. By the way, all the papers we have chosen for you are those papers that have open code. Most of you will be running simulations and you will need resources. We cannot promise to give you resources. We hope that you bring your own resources from your department, and we will do our best to find ways to help you and tie you to some of the labs or to AWS, etc. Okay, so the final grade will be basically 50% for the presentation quality and 50% for the research quality that you did on top of the existing paper. As for the course material, the lectures will be recorded as we are doing now, and they will be shared with the rest of the world and with you. I'm not planning to share the slides as of yet, but it might change. But again, if you have the videos, it's equivalent. And that's it, I guess. I don't think we'll have to go here into the people to follow. This list appears on the webpage or sources. I will mention these sources as I run through the course, etc. Questions so far?
Yeah. Mickey, can you give some guidelines to how you're going to grade the second part, the other 50% of the work that goes beyond the original?
It's a function of how novel the extra work is, how dominant it is. I can tell you that in the previous year, some people did work that could be published in a paper. Others did something that was nearly trivial, and all of them passed well the course. But clearly, the one that creates something that is almost publication worthy will get a higher grade. Okay, I mean, I cannot give you complete guidelines, but it depends on the amount of work, the novelty of it, and maybe how close it is to be publication worthy. Okay.
Yeah. Okay.
Other questions?
Mickey, you want us to present in English?
No. You are welcome to do it in Hebrew if you want, but if you choose to do it in English, no objection there as well. Okay, good question. Okay, let's move on. So here is the general plan for our course. We just started with the description of the administration. I'm moving in a second to the mathematical review, which will take 10-20 minutes. And then we start the material. And today we will dive into this chapter, still not talking about diffusion. This chapter is about background. Much more about it will be said when I step into these slides. And then chapter 3 will be the actual introduction to diffusion models. Slowly and gradually we'll get to the Langevin dynamics and whatever comes next. We'll talk about DDPM, the most popular algorithm and the most familiar one. We'll talk about acceleration methods, because diffusion methods, you should know, are very slow, and this is truly annoying. So people keep searching for ways to speed it up. In this chapter, we will talk, among other things, about the nested diffusion. This is the work of Noam. We'll talk about guided diffusion. This is a very important topic. It's used extensively. We'll talk about how to actually navigate the diffusion towards our goals, and then talk about inverse problems and how to solve inverse problems with diffusion. Here I will be talking about the revolution that took place that I mentioned. Noam will talk about deriving diffusion models from SDE and ODE. And with this, we will end the course. These topics I'm not going to cover, or at least this is the general plan as of now. And one last thing that I do want to mention is the fact that diffusion models is a very hot topic. It's very young and it's very, very dynamic. It keeps moving. Here is an illustration. This is a graph that shows the accumulated number of papers in arXiv that were published on the topic of diffusion models. At the moment, this stopped at 2023 February. We are now almost a year forward. So at the moment, it stands of something like 1,200 papers. 1,200 papers in a period of basically 2-3 years. Most of the activity took place in the past 2 years. This is a graph taken from this blog. And many people are playing with this information because it's really fascinating. The field is crowded, loaded with papers, loaded with researchers that are basically turning every possible stone. If you have an idea, you can bet your life that someone else is working on it. And if all this is not enough, let me tell you one more thing. 2 years from now, this field will become obsolete. This course will be obsolete. In what sense? In the sense that everything that will be described in this course will be changed to something better and different. And this is fine because this is the path. This is how research is evolving. So just bear this in mind. Okay, let's go to the mathematical review. And again, you can stop me anytime with questions. I'm going to start with some basics with probability theory. Most of the course will be concentrated on images or random vectors X in Rn. So X is an image. It is assumed to be a random entity. N here is the dimension. It could be 1,000, it could be 10,000, it could be 1 million, and all of them are fine. And this vector has a probability density function, a function P of X that assigns a probability to the event of X happening. Okay, let's talk about this function P of X. PDF, I'll keep mentioning the term PDF, so probability density function. So clearly, this is an illustration of such a PDF for a scalar X. For a scalar X, this function can take any shape, but it is clearly non-negative. You cannot expect a probability to be a negative. One thing that is very clear is that the probabilities are always non-negative. But here is one thing that is counterintuitive. These probabilities can go above 1, okay? They can have actually values above 1. Think about a Gaussian. If you have a Gaussian distribution of a scalar, if the sigma is very, very small and the Gaussian is narrow, it's going up way beyond 1, okay? So where is the normalization here? Here it is. The event of infinitesimal range of x's multiplied by their probabilities, this is something that is always smaller than 1. And in fact, the integral over this is exactly 1. Just to say that the whole events together of getting x's in all the domain of x's sum to a probability of 1. This is an event of probability 1. Okay, if your image is a deterministic image, it's not random, it's a fixed given image, x naught. I refer to x0 as x naught. So if it is such a fixed image, it still is random, but it has a delta function as a density function, as a probability density function. So this function is a probability density function of a deterministic event that happens in x naught with probability that goes to infinity and zeros elsewhere. If you have two vectors, x1 and x2, they might be of a different length in general. You can talk about their joint PDF. The joint PDF is the probability of the event together of getting x1 and x2. And so when you take this joint probability, joint PDF, and integrate with respect to one of the ingredients, in this case x2, you basically do something that we will be calling marginalization. You remove the appearance of x2 and you end up with a probability of x1. Marginalization is something that we will do something like 1 million times in this course. So keep this in mind. Here is an axiom in probability, and the axiom says that the conditional probability of x1 given x2 is in fact the joint divided by the marginalized version. So P of x1, x2 divided by P of x2 is the probability of x1 given x2. And in fact, immediately follows from here the Bayes formula or the Bayes rule. Look at this, P of x1 given x2 equals to whatever you see here. Bayes rule is a terrific concept, terrific formula for replacing order in conditionals. If you would want to take x2 given x1 and replace it with x1 given x2, this is exactly the formula for you. What is the connection between Bayes and the previous claim? What do you say? What is the connection between this formula and what we have seen before? Someone, please. Take this formula and multiply. Yes, Adas.
IID or not?
No. Look at this.
Okay.
If you take this formula here, the conditional probability, and you multiply both sides by P of x2, you end up with P of x2 times P of x1 given x2 is the joint. But this is also true that P of x2 given x1 times Px1 is the joint. So you take these two equalities and you play with them, you end up with the Bayes rule. Very simple. Okay. Another thing, sometimes these two elements, x1 and x2, are statistically independent. If this is the case, then the function is separable. So basically the probability, the joint probability is a multiplication of two separate probabilities. Lovely. We proceed. If you have a chain of vectors of the same length, x1, x2, x3, all the way to xn, you can talk about chaining them in order to define their joint probability. So the joint probability of all these together is the probability of x1 times the probability of x2 given x1 times the probability of x3 given the previous two, etc., etc. So nothing is lost here. This is always true. But of course, this is really cumbersome because the later pieces here have very complex conditioning. If you are lucky and you are looking at a Markovian chain, this conditioning becomes much simpler. It looks like this. Instead of P of x3 given x1 and x2, you need only x2. Why? Because knowing x2 in Markovian means that I don't need to know x1. All I need to know is the previous vector. Or if you like, this is the general formula. P of xk given the rest is always equal to P of xk given xk minus 1. Just tell me the previous vector and you told me everything there is to know. Why this is important? Because in diffusion models, we will lean heavily on Markovian chains in those iterative processes that we will be developing. Okay, and here is an illustration. Suppose that I want to draw a random set of vectors from this joint. Here is what I'm supposed to do in the Markovian case. I draw x1 from its probability, use it to draw x2 given x1. Given this, I draw x3 given x2, etc., and propagate this way up to xn. The vectors I'm getting are basically a fair sample from this joint probability. And I proceed. Suppose that you have two vectors that are statistically independent, x1 and x2. They are of the same length, and they have two different PDFs, P and Q. And now someone takes these two realizations of x1 and x2, just draw x1, draw x2, sum them, and creates a new vector z. Clearly, z is a random vector. What is the distribution of this vector? What is the PDF of it? Well, the claim is the distribution of z is nothing but the convolution of the two, P and Q. P and Q. It should have been Q here. Okay? Let's prove this. Very easy to prove. What is the probability of a vector z? You have to go through all the possibilities of x1 and x2 that sum to z. So let's do that. Let's write this integral. Here it is. I'm integrating over all the x1s. I remind you, those are independent vectors, x1 and x2. So the probability is basically multiplication of two separate probabilities. So it's the probability of x1 times the probability of z minus x1. So basically the sum of this and this is always z. And by integrating over all the x1s, I'm basically scanning all the possibilities of getting x1 and x2 that they sum to z. Now look at this expression. This is a classic convolution. Okay, so this is a convolution, and this is a well-known result in probability theory. Good. I remind you, you are welcome to stop me anytime with questions. Let's talk about expectations. If x is distributed along P of x, this is the PDF of x, and you bring me a deterministic function over the unknown random vector x, f of x, then we can talk about the expectation of f of x. The expectation in this is defined as this integral. You basically run over all the x's, compute f of x times the probability of getting that x, and sum everything. General expectation. Expectation is linear. So expectation of sum of functions is the sum of expectations. It immediately follows from the definition. And you are most familiar with two expectations that we use very often, the mean of a distribution, which is simply expectation over x itself, and the covariance, which is the expectation of this multiplication. You take the vector minus its mean, multiplied by the transpose of the same thing, and if you do the expectation, you end up with a matrix that is the covariance. If x1 and x2 are uncorrelated, then the expectation of their inner product is in fact the inner product of the expectation. So you can squeeze in the e, the expectation inside the multiplication. In fact, this goes in the other direction as well. If this is true, then x1 and x2 are necessarily uncorrelated. Now, there is always a confusion between uncorrelated vectors and independent vectors. If the vectors x1 and x2 are independent, the same happens, but it's not working in the other direction. Knowing that this is true, this separation here, doesn't imply independence. It just implies uncorrelation. Okay? What is the exception to this?
A Gaussian case.
Exactly. Okay. And we'll talk about the Gaussian in a second. Let's talk about conditional expectation. Just like we have defined expectation, we can define conditional expectation. So now we don't talk about P of X, we talk about P of X given Z. So the expectation of X given Z is very much like what we did before, with one distinction: the probability itself is the conditional, and that's all. Now, from the formulas I've shown you 3 slides ago, this conditional is nothing but the joint divided by the marginalized. So, and why am I bothering with this equation? For the next step that I'll be taking. Okay. So there is a lovely property called the smoothing property. I don't think we will have a use for it, but it's good to know. If you have to understand one thing. This conditional expectation, once you compute it, it's a function of Z, okay? It's an expression where Z is playing a role because it's given Z, so Z will have some effect on the outcome. What if you take now the expectation of this expectation? The expectation this goes through yet another external expectation with respect to all the Z's. And the claim is, it is simply the mean of X. Let's prove this. Very simple to prove. Here is the proof. I remind you, the inner part, the bluish part here, is nothing but what I just wrote here. So I'm taking the inner part E of X given Z, and I'm translating it into an integral. The outer part is simply doing the expectation with respect to Z. Take the horrible expression, whatever it is, multiply by P of Z, multiply by dZ, and integrate. Now, obviously, you see that PZ can go inside and cancel the denominator, which is exactly what you see here. So we have double integral over X and Z, and this is the expression. Now let's change the order of the integration. Let's actually do the inner integration with respect to Z and the outer with respect to X, which is why X is here. Look at the bluish part here. What is it? What is this bluish part? I'm integrating Px and Z with respect to Z. This is known as
Marginal distribution.
The
marginalization. It's a marginal distribution. It's P of X. So here it is, P of X. Now look at this. What is this? This is exactly the expectation of X. This is the mean of X. Okay? This is the mean of X, which is just what we claimed. So this is the smoothing property. Okay. Let's talk about Gaussians, because they will be the stars of this course. Everything we will do, we'll talk about Gaussians. So if X is a random vector of Gaussian distribution, it really means, or normal distribution, it really means that this is the probability density function of it. We have an explicit form for it. Look, it's the mean mu and the covariance sigma that are playing a role in this expression. This horrible expression here is nothing but what you need in order to make sure that the integral is 1. And this is a shortcut notation that we will use a lot. So when I'm telling you that X is normal, I'm writing N for normal of the unknown X with first moment mu, second moment sigma. And this is the expression. A few words about these vectors. Uncorrelated Gaussian vectors are also independent. So this is exactly what we mentioned before. Independence and uncorrelation are 2 different notions. In this case, they fully overlap. Okay, if you have a random Gaussian vector of specific mean and covariance, and you apply AX plus B on it, A being a matrix and B being a vector, the vector Z is also Gaussian. And it's very easy to compute the first and second moments. Here they are, very simple to get. Okay, and they emerge immediately from the definition of the expectation. If you have 2 vectors, x1 and x2, of the same length, and they are independent or uncorrelated, who cares? It's the same thing. And you are summing them up. What will you get as the distribution of the sum? What do you think? I'm summing 2 random vectors that are both Gaussian and independent of each other. What am I getting? Yeah, please.
A Gaussian random variable.
I'll get a Gaussian, not just a Gaussian. The Gaussian will be very simple. The mean will be the sum of the means. The covariance will be the sum of the covariances. Notice that just 2 slides ago, I told you that when we take 2 independent vectors and sum them, we get a convolution of the distributions. But here is what's happening here. Convolution of a Gaussian with a Gaussian is a Gaussian. Okay? So this is exactly what happened here. I'm moving to basics in information theory. And for that, I'm departing from continuous PDFs and talk about discrete ones. So imagine that X now is a discrete variable. like throwing a cube. And the cube has C faces, capital C faces, 6 in regular cube, C in the more general case. Every face has a probability. P of X equal K has a probability PK, okay? And of course, all those probabilities sum to 1. All of them are non-negative and they sum to 1. This is obvious. In information theory, it deals with the question of quantifying the information that is carried by such a random variable. So here is sort of an axiom that says, if X assumes the value K, the amount of information that you are given by knowing that this is K, the amount of information is actually proportional to log of 1 over this probability. Where is it coming from? So think about the following. Imagine that this probability here is 1. What does it mean? It means that there is no randomness. Even without knowing anything, I knew that X will be K. If the probability is 1, it really means that all the rest have 0 probability. So no information. There is no information. So if this is 1, 1 over 1 is 1, log of 1 is 0, the amount of information is 0. If on the other hand, the probability is very, very small, something like 0.001, it really means that this is a rare event. So by telling me that X equals K, you gave me a lot of information because something really rare just took place. So the 1 over this probability will be a large number, and log of it will be a large number. And this is the amount of information that is carried by the fact that X equals K. Now, why do we carry the log? Simply because if I give you 2 random events, X equals K and X equals J, the probability of the 2 together, if they are IID, is the multiplication of the probabilities. But in terms of information, it should be the sum of the information pieces. So moving from multiplication to sum is exactly achieved by this log. Okay? Now, nobody cares about what I've just said. People always start their story by talking about the entropy. The entropy, as Shannon defined it, for a random variable X that follows this distribution, is the expected information. This is it. This is the formula for the entropy. You take the information for each of the Ks and you multiply by the probability of this event happening, and you sum over all the capital C pieces, and you get what is known as the entropy. Look, the base here is 2 to illustrate the fact that we are talking in terms of bits. Okay? Something about entropy that you should know. It's always non-negative. In fact, it is exactly 0 if the distribution is deterministic, which means one of the probabilities is 1 and all the rest are zeros. In this case, just go ahead and check. The entropy is 0 to tell you, hey, you have no information to share with me. I know exactly what you are even before you told me anything. The other extreme is the upper bound here. The upper bound is log 2 of C, and this takes place when all the probabilities are 1 over C, which means all of them are equally likely. In that case, the amount of information is the maximum you can have. Okay. Now, why are we bothering with entropy? Because we will need something called the Kullback library in a minute, which is very often used in machine learning. So just before going there, let's do a simple step of moving from the discrete to the continuum. So notion of entropy can be extended to the continuum. So now imagine that we are back into vectors X of Rn that have a probability density function P of X, and those are continuous values. You can generalize the notion of entropy to what's known as the differential entropy. Simply replace the sum with an integral, and that's it. Looks so simple. The problem with this expression is it may get negative values, which is totally counterintuitive. And why can it get negative values? Because I told you in the very beginning, P can actually go beyond 1 in the continuous case. And so these negative values are creating a lot of confusion, but this notion of entropy makes a lot of sense and can be used and is being used. Okay, here's another property, very interesting property. Suppose that you have a scalar X that is random. Now, nobody tells you how it is distributed. You just know that it is random. Moreover, you know that it has a mean mu and a standard deviation sigma. Now, there are infinitely many possible distributions that will obey these two moments. Among all of them, the one that will give you the maximal differential entropy is the Gaussian. And here it is. This is the amount of, this is the entropy in this case. Okay, there is a closed form expression for it. One thing to notice here is that if sigma is very small, this whole thing may become negative, and this is perfectly fine. Okay, and now let's talk about Kullback-Leibler. Kullback-Leibler is an attempt to come up with an assessment of a distance between two distributions. So you give me two distributions, P of x and Q of x, and I'm supposed to tell you how far they are. And so Kullback-Leibler is a divergence measure. It's not a distance measure, and I'll explain why I insist on this term. And here it is the definition, okay? Kullback-Leibler between P and Q is the expectation over all the x's that are drawn from P of this expression, or just put in other words, simply this integral. Integral over P of x times the log of the division of P by Q. And you sum over all the x's. Kullback-Leibler, few properties. First, it is always non-negative, which is great news. Distance between two distributions should not be negative. However, look, it's not symmetric. KL of PQ is not KL of QP. Sometimes people define the symmetric KL by defining KL as KL of PQ plus KL of QP, and then everything is well-behaved and symmetric. But in most cases, people do not bother. Another property is that KL becomes zero only if the two are the same. Sorry. Notice that if P and Q are the same, log of this becomes log of 1. Log of 1 is 0, so who cares who P of x? You end up with 0. So it actually works in both directions. If it is 0, they are the same. If they are the same, it is 0. In the case of two Gaussians, and this is critical for us, the distance between these two Gaussians that have general means and covariances, there is a closed form expression for the KL. And we will be using it. In fact, we might even use it today. Okay, we might be using it today in the context of variational autoencoders. Okay, so this is the KL. One last thing I want to mention is the mutual information. If you have two vectors, x and z, they don't have to be of the same length, but let's simplify things. This is their joint probability. So this is, by definition, the mutual information in x and z. Okay, look at this. Okay, looks very similar to KL. It's a different KL. It's a KL between the joint probability and the joint if they would have been independent. So basically, you are measuring the distance between two versions of distribution of x and z, one if they are independent and one if they are dependent. So basically, joint information here, or mutual information, is a way of quantifying how dependent two variables are. Properties of this. For example, if x and z are totally independent, then the information is 0. And actually, it works in the other direction as well. The information, look at the expression, is symmetric. Replace the order between x and z, and you get the same thing. So it is a symmetric measure. Information we mentioned is 0 for totally independent vectors. This is also the lower bound. The upper bound is the differential entropy of the smallest of the two, x or z. In fact, if z is a deterministic function of x, then the information in x about z is itself age of x, and that's all. Yes, one more thing, and with this we will finish. At some point, we will talk about Wasserstein distance. Please do not be alarmed, but this is something that people use oftentimes, so we do have to mention it. Wasserstein is another way of quantifying distances between distributions, P and Q. In our case, we'll talk about Wasserstein 2. So here is the definition. It goes like this. You have P and you have Q, and you are wondering how far they are. You are going through all the possible functions G of x and z that are valid joint probabilities, such that the marginal with respect to z is P of x, and the marginal with respect to x is Q of z. Okay, so think about 2D. The function gxz is the 2D. You project horizontally, you get P of x. You project vertically, you get Q of z. There are infinitely many possible functions that describe joint distributions such that the marginals are P and Q. Among all of them, minimize this expression that creates the shortest possible path of replacing x's by z's with this joint probability. So if you have a joint probability that is nearly diagonal, this is the ideal case to have, okay? And few properties about this. This is basically, by the way, optimal transport. It is also closely related to Earth's moving distance that has been used for years in different contexts. If the two functions are the same, this is 0. This is a proper distance, okay? It obeys all the axioms that distance should obey, like convexity, etc. And again, here, in the case of two Gaussians, it has a closed form. It has a closed form. Look at the closed form. It's actually very intuitive. It says the two Gaussians have two different means, mu p and mu q. If the two are the same, this element drops. They have two separate sigmas, sigma p, sigma q. So, and this is actually sigma p, sigma q to the power half. So if the two are the same, you get sigma p plus sigma p minus twice sigma p, again 0. So you end up with 0 if the two are the same. That's it. This is the brief mathematical review. And at the moment, what I'm suggesting is to take a 10 minutes break. Let's meet at 5:30 and proceed. Questions before we go? Questions? I know I went very fast through things, but things will be more relaxed from now on. Maybe. Questions? Okay, so let's have a 10 minutes break. Bye. Okay, we proceed with the material by going into this chapter of background. And in this background chapter, I'm going to talk about the importance of P of X for images, how central it is in doing almost everything that we do in image processing. We'll talk about the evolution of how P of X was guessed or devised during the classical era, and that means over 5 decades up to 10 years ago. And then we'll talk about the deep learning revolution. Now, I'm guessing that today we will not get to the third part, which is the most interesting part, but hey, it will wait for us in the next meeting next week. So let's just go slowly, and I remind you, stop me anytime with questions. Don't write in the chat because I don't see it. I'm so concentrated on the slides that I don't see it. So if you have a question, just just unmute yourself and ask a question, okay? So let's talk about the importance of priors in image processing. And I'm going to start with a virtual experiment. Imagine the following. Imagine that I have a data set of many natural images, and I'm breaking them down to patches of size 20 by 20. You know what? Fully overlapped patches, all the patches in these images, and I'm talking about billions of patches, okay? I have many such patches, and of course, every one of them is a vector in R400. In fact, every vector of this sort is actually also sitting in the cube 0 to 1 to the power 400. Why? Because these are pieces of images, and the gray values are between 0 and 1. This is what I'll assume. 0 being black, 1 being white, and things in between are the grayish. Forget about color. Let's assume that this is not colorful images. And so I have billions of vectors of dimension 400 that are sitting in a cube of dimension 400. Okay, so I'm taking every one of those patches and putting a point in this cube, and slowly and gradually the cube is loaded with those billions of points, reddish points. And now let's take a step back and look at what we have just created. Let's have a look at this 400-dimensional space and the cluster of points that we have injected into it. What are we expecting to see? Any ideas, please? What do you think? What will be, what if we could look at the dimension 400, what could we see there? Any guesses? Let me ask you a guiding question. How much of the volume of the cube will be occupied by these patches? How much relative to the whole cube volume will be occupied by these points?
Would be almost empty.
Almost empty. It will be almost empty. Yes. Basically, the first thing that will jump to your mind is the fact that this is total emptiness, deserts of nothing, large regions where patches never visit, which means These are regions that for patches that correspond to patches that cannot exist in natural images. And it is happening. Okay, there will be concentration of patches here and there. Then we will see something very interesting happening. These patches will concentrate in all sorts of filaments or manifolds or hyperplanes, structures of low dimension within the embedding space. The space that is embedding here is the 400 space, and the actual dimensionality is 10, 5, depends on the point you are looking at. And I'll come back to this low dimensionality in a minute to make it clear. Okay, so this is what will happen. What have we done here? Of course, the concentration of points will be different from one point to another to manifest the fact that some regions are highly popular, others are less so, quite obvious. What have we done here? In fact, what we did is to build an empirical description of P of X for image patches of size 20 by 20. We actually built a histogram in 400 dimensions of the density function of these patches, P of X. Okay, let's talk about this low dimensionality that I mentioned before. Let's illustrate it through an example. Imagine that I take a specific patch, any patch, X naught. Okay, now I open a window around it, a sphere around it, a sphere, and I grow the sphere, grow and grow up to the point where I have exactly 1,000 neighbors next to me. Remember, I have billions of patches, so I just 1,000, it's a very small sphere of radius delta. I'll take all these 1,000 examples and build this matrix. This matrix is of size 400 by 1,000. Every column is one of the examples, one of the red examples, one of the red neighbors, minus the vector X naught that started it all. So we have a lot of vectors of length 400, 1,000 of them. I'm looking at this matrix E, and I'm wondering, what kind of behavior can I expect? What do you think? What can I expect?
Kernel dimension is very large.
What do you mean by kernel dimension?
Like a null dimension. The eigenvalue 0 was probably very
okay, wonderful. I remind you, this is a non-square matrix, so we cannot talk about eigenvalues unless you are talking about E transpose. But yes, you are totally right. Let's do SVD on this matrix. Remember, singular value decomposition. And we will discover this matrix is very likely to be of very low rank, effective rank. What does it mean? It means that the first 5 singular values will be non-zero, positive, and dominant, and the rest will be nearly zeros. What does it mean? It really means that if you stand on X naught, there are 5, 6 directions in which you can go from one patch to another patch to another patch, patches that are all valid and okay. But if you go outside of these 5 directions, you fall immediately into the desert we mentioned before. Okay, this is the low dimensionality that I refer to. Now, obviously, it will be low dimension, but the orientation of this hyperplane will be different from one X naught to another. So it will be a manifold that does all sorts of things. I hope you see my hand. By the way, what I'm just describing to you here is fundamental to all signals. This property of having a low dimensional structure within the embedding space is the reason why we have signal processing, is the reason why we have image processing, is the reason why we can do machine learning. Without this property, nothing could have been done. And so it's true not just for images, it is true for audio, it is true for seismic data, it is true for text files, it is true for any piece of information because the data we work with has structure in it. The structure that enables its compression, its denoising, it's whatever you want. This is the origin of our ability to do signal processing or machine learning. Okay, so we spoke about the orientation. So let's talk about this function P of X. What I've just described is a simple experiment with patches of size 20 by 20. You can repeat it. It's virtual. You are allowed to do it on complete images, large images of size 1,000 by 1,000. In fact, everything I said will only strengthen. So the compression effect will be much tighter, much stronger. And yes, it applies to other data sources, financial data, seismic data, biological signals of all sorts, EEG, ECG, etc. And in this course, I will concentrate on images, but please keep in mind, much of the things we will be describing apply to other signals with proper adjustments. Now imagine this, a function P of X. You feed it with an image, it computes something and comes up with a probability that tells you how probable this image is. This is amazing. The question is, what can you do with this function? And the answer is everything. This function is the center of everything we do in machine learning, in image processing and signal processing. And now let me spend several minutes convincing you that this claim is actually true. So assume that you have images and you do know P of X, and let me show you what you can do with it. Let's start gradually. Let's start by removing noise from images, okay? So here is the game we are playing now. There was an ideal image X0 that is a good-looking image. It is sitting, it has a high probability, let's say, or reasonable probability, definitely not zero. Someone took this image, added noise to it. Look, at the moment I'm thinking about the noise as a bounded energy noise, okay? And I'm getting Y. And the question is, how can I clean the image Y and come back to X0? This is my goal, recover X0, X0 from Y. Now remember, I do know P of X. This is the game we will be playing. So here is a geometrical description of the problem. This reddish bright line is the manifold of good-looking images. X0 is sitting here on top of it. You don't get to see X0. You get to see Y, which is epsilon away from it. Okay, this circle has radius epsilon. So instead of getting X0, I'm getting Y. And given Y, I'm trying to make my way back to X0. How can I do it? And let's be even more specific. How can I do it while knowing P of X? Okay, just before going into the answer, I want to draw your attention to the following assumption that I made, which might annoy you. I drew Y here. You could have drawn Y here, right? Do you agree? Of course. So why have I chosen not to put Y here, but here? Is there any justification to assume that Y will be more likely to be here than here?
Because the dimension of the manifold is very small compared to the dimension of Y.
Exactly.
And so it's...
So if someone that adds the noise just draw the noise at random, the chances of falling on the manifold, I'm telling you, if this happens to you, go and buy a ticket for lottery because you're going to make billions. Okay, it never happens. This is 5, 10 dimension. The remaining, in the story of the 400, the remaining dimensions are all outside the manifold. Or put differently, you do know that the noise typically is uncorrelated. Y minus X0 is the noise. The noise is uncorrelated with X0. The image and the noise are uncorrelated. Being uncorrelated means that I'm expecting the vector here to be orthogonal to the manifold. Okay? Forget everything I said. Let's move on. Just live with the fact that Y is here and not here. Okay, good. So now given Px, I want to recover X0. Here is what I'll do. Remember, all I have is Y. So I'll draw a circle, a sphere. Come on. Okay, I'm drawing a sphere around Y with radius epsilon. It contains many, many possible candidate solutions X0s. Okay, and among all of them, and per each of them, I can actually check what is the probability of that point. I will go and search for the point X that has the maximal probability within this sphere. And when I finish, I end up with a vector X0 that is very close to the X0 that I started with. Okay, this is known as the map estimation, maximizing the probability of the points within the sphere that is epsilon away from Y. I'm using P of X, just as expected, and I'm capable of cleaning up the noise. By the way, you might get the impression that I'm getting back exactly X0. It never happens. I will get something close to it, hopefully, and you can actually bound the distance between the two. But I'm getting close to it. I'm actually capable of cleaning noise. Why? Because of the knowledge of P of X. Okay? In fact, there is another tool, less intuitive at the moment. And the other tool is MMSE, minimum mean squared error. It basically says, you just created a sphere of all candidate solutions. Go ahead and compute the expectation over this sphere. Expectation, basically average all the possible X's in this sphere. Here it is as a formula. You take all the x's in this sphere, you average them, but weight them by their probabilities. So obviously you will give higher weight to this region. And so you will concentrate towards the true x naught, which makes a lot of sense. We will talk about the MMSE a lot in this course. And in fact, in 2 minutes, I'll make it much more precise. But at the moment, this is all I want to present. So cleaning up noise from images is doable if you know P of X. Great. In fact, let's generalize this. We can move from denoising to other inverse problems. So this is denoising. You had a noisy image and I'm cleaning it up. But I can actually do deblurring, where the image is blurred and noisy, or in painting, where portions of the image are masked out and I need to revive the values, or demosaicing, where the image that I'm supposed to take is color image, RGB, and per each pixel, I'm getting only one of the 3 values because the sensor cannot give me the 3. So I need to guess the other 2. This is a well-known problem in image processing because every camera has it. Your cell phone uses it, okay? Your cell phone has a sensor. The sensor measures 1 value per pixel. It could be either red, green, or blue, typically using this mask, okay? And the rest of the values, the other 2/3, is basically interpolated using some sort of solution of inverse problem. Tomographic reconstruction, where you show me the projections and I need to give you the intersection of a body. Or super resolution, where there was a high resolution image that someone took and squeezed and reduced size and blurred maybe, and I need to enlarge it and create a crisp outcome. In all these problems, the connection between x naught, the ideal image, and the measurements y is this relationship that says x naught went through some degradation operation, C, plus additive noise, and you get y. And now, given y, and knowing C, please tell me who x naught is. This is inverse problems, inverting the degradation. So can we solve inverse problems using P of X? Let me convince you that this is indeed the case. So here it is. Suddenly the slides go slow. Oh my God. It collapsed. Okay. So there was an ideal image x naught that went through a degradation operation C, and I'm adding some sort of noise, limited and bounded energy noise, and I'm getting y. And the question is, how can we recover y from x naught? And again, the game here, can you use P of X in order to do this reconstruction, this restoration? Just as before, here is what happens. You have to understand y might be of a different dimension than x naught. For example, if this is super resolution problem, y is a smaller image, x naught is a bigger image. So they are not talking in the same language. So the first thing I'm doing is to apply C pseudo inverse on y in order to be in the same space. And here it is, a sphere of radius epsilon, okay? Now the recovery using the map estimate, for example, will be this. Don't even bother with the geometry. Just look at the equation here because it is so intuitive. It says the following. You gave me y. I'm searching for x such that if I degrade it with C, I'm getting something that is up to epsilon away from y. Now, there are infinitely many possible such x's. Please give me, among all these x's, the one with the maximal probability. This is map all over again. And it makes a lot of sense. And by the way, the shape of this body of possible solutions, the feasible solutions, is this ellipsoid. This is exactly the ellipsoid you see here. So among all these ellipsoid points, x, give me the one with the maximal probability. And assuming that I can solve it numerically, I have an amazing solution. In fact, here as well, I can come up with MMSE, but I'm not going to bother because now let's make things far more precise, okay? So I'm repeating everything I did for the denoising and inverse problems, but now I'm doing it more precise because we will need it in this course. So imagine that the noise is not just bounded energy noise, it's a different kind of noise. It's a noise that comes from a Gaussian distribution. Zero mean IID noise, okay? It's a typical assumption, we do it a lot. So now we are trying to recover x naught from y. How do you do it? There is a line of thinking in inverse problems known as the Bayesian point of view. And the Bayesian point of view says what you need to do is to formulate the conditional probability P of x given y. Now, think about it. It makes so much sense. P of x given y. First of all, y is indeed given. So yes, given y. And this function, what it says is, for all the x's that could be there, I will assign a probability for them to explain y. P of x given y. And now if by some miracle, you have this posterior distribution, P of x given y, here is what you could do. For example, using the Bayesian approach, you could do the map. You could actually say, give me the x with the maximal probability, given y. Given the measurements y, what is the x that has the highest probability of explaining y? It makes a lot of sense to use this. This is the map. And you know what? Let's now develop this. Remember, I can use the Bayes rule and replace the order between x and y. So let's do that. So I'm replacing xy with yx times px divided by py. This is the same thing. Now, I'm supposed to find the x that maximizes this, or the x that maximizes this. Now, notice that the denominator plays no role, okay, because it's a constant with respect to x. It's a number, so we can omit it. And instead of maximizing the multiplication, I can also maximize the log of the multiplication, or minimize the minus log of the multiplication. And this is it. This is exactly equivalent. So instead of maximizing the multiplication of the denominator, I'm minimizing the sum of the logs in minus sign. And here, I want to draw your attention to the appearance of P of x. P of x, the function that describes the probability density function of images, has an important role. Here it is. It is being used. But what about the bluish part here? What do you think? What is this bluish part? Is it complicated to get? Anyone?
No, because you have a model of the noise.
True. Be more specific.
What
What is P of y given
constant.
x? What is P of y given x?
A Gaussian with its mean being x and its variance being sigma squared.
Almost exactly right. Look at this equation here. P of y given x means now x is given, x is x naught. So if x is given, then cx is also given, okay? Now you take a vector that is given to you, a deterministic vector, and you add it to a Gaussian. What do you get? You get a shifted Gaussian. So y is a shifted Gaussian, which is exactly what you described. So basically, the bluish part here is, forget about the log here, just look inside. It's a Gaussian. It's a Gaussian with mean cx, the mean cx, and the variance is the variance of the c of the v. So this is the expression. You need the minus log of it? Go ahead and take a log. The log cancels the exponent. There is a constant here that nobody cares about. And you end up with this expression. So now I can replace the bluish part with this term. So here we are. I remind you what we are doing. We are solving an inverse problem with Gaussian noise as a contamination. And we just discovered that the map estimate is the minimizer of this expression. Now look at this. This is a classic least squares with regularization. This is the least squares that says, find me the x that minimizes this expression. As it so happens, there are many such x's, but give priority to x's that have higher probability, okay? So this is the map estimate. Least squares plus regularization that draws its force from knowledge of P of x. Great. Let's now do something different. Let's do the minimum mean squared error estimate. The minimum mean squared error estimate basically says, listen, I want my estimate x hat not to be the highest probability vector, but to be the one that will give me the smallest L2 error in expectation. As it turns out, this is it. It is a conditional expectation. This is why I mentioned it in the review. It's a conditional expectation. It's E of x given y, or this formula. Where is it coming from? Let's prove it in 2 lines. It's very simple. The minimum mean squared error estimate is basically x hat as a function of y, because it operates on y, does all sorts of computations, and comes up with a solution. And it says, listen, my distance from the true x on expectation, the distance L2, in expectation given y, is to be minimized. So let's write down the expression explicitly. It's x minus x hat, L2 norm, times the probability of this x given the y, dx. This is the animal that they are trying to bring to a minimum. Okay, looks horrible. Actually, very easy to minimize. What did I want to say here? Yes, I omitted the dependence on y, but it's here inside. Don't be alarmed about it. Okay, I want to minimize this. So let's take a derivative of this expression with respect to x hat. And when you take a derivative, the derivative steps inside, derives the L2 term, and you get that all this part is simply replaced by 2 times x hat minus x. Here it is, 2 times x hat minus x, p of x given y, dx. And this should be 0. Organize terms, and notice that x hat can fall outside of the integral, and you end up with this formula. X hat should be integral of x, p of x given y dx, this is denominator, divided by integral of p of x given y dx. Now look at this. This is just 1. Integrate something that is a probability density function over all the x's, it's just 1. So it vanishes, and you end up with a nominator, which is what? The conditional mean. Now, a little bit of intuition. Coming back to this formula, what am I telling you? I'm telling you the following. Imagine that you have the following inverse problems. I'm giving you a very small image, and I'm asking you, what is the bigger image that can explain it? Now, there are infinitely many possible large images that can explain it. The minimum mean squared error says, listen, bring me all the possible images that can explain it, and I will average them. Expectation is all about averaging. I will average them. Here is a weighted average because I'm giving per each image its probability of being the proper explanation. And while averaging, I'm creating a solution that is somewhat blurry, yes, but it is the best in terms of mean squared error. And by the way, people who are practitioners in deep learning are familiar with this property. When you train a deep neural network to do super resolution, and your loss is L2 or L1, and you are doing super resolution, so small images translated into a bigger image, you typically tend to get blurry outcomes. Why? Because of this. Because it actually creates the minimum mean squared error, which is by definition blurry, as it averages many, many possible solutions. Okay. Now I remind you of the main theme of our story. It's not about MMSE or MAP. It's about the importance of P of X, in order to solve problems. And what we have convinced ourselves so far is that if you know P of X, you can solve a large family of inverse problems very effectively. Lovely. Let's move on. Can we compress images using knowledge of P of X? Let's see what is the connection between P of X and the best compression algorithms that people can come up with. Okay, so here's the game. You are giving me images that are drawn from P of X. P of X is known to me, and I'm supposed to compress them. That means you give me a budget of capital B bits, and I'm supposed to represent your image with the minimum possible damage, error, with these B bits. Okay, how do I do that? Here is an interesting fact that people are not aware of. Compression of images, compression of data, is all about tessellation. It's all about slicing the high dimensional space where images are living into tiles, into regions. You break the whole space into exactly 2 to the power b tiles. Why 2 to the power b? Because if this is the number of tiles, then the address per each tile is exactly b bits. And the compression mechanism goes like this. You gave me an image. Suppose that God gave me the tiling, okay? The tiling is ready. I'm asking which tile am I falling into? And you tell me, oh, you are in tile number 377. Okay, I'm sending to the other side B bits that tell you the number 377. You know that I fell inside this tile. You draw out the center of this tile and tell me, this is your image. And of course, it's not your image, but it is not far off, which is exactly how compression works, okay? So designing a good compression is all about designing the tiling so as to minimize the error. So let's write down the expression. Here is the expression that people use in order to do this optimal tiling. It basically says the following. I'm optimizing over all the possible tiles and all the possible representation vector xk's. Those are the red points here. Every tile, in the center of it, there sits a representation vector. I'm optimizing with respect to the tiles and the representation vectors 2 to the power b such unknowns, and per each tile, I'm running over all the x's inside the tile and integrating the error. And the sum of all this is the overall error. This is the expected error. And by minimizing it, I will design the ultimate compression algorithm. Looks frightening, especially because the tiles themselves and the borders between them are so complicated, but actually it's much simpler. Turns out you don't need the borders. All you need are the red point, because the actual compression works in a slightly different way. When I compress an image, I do not search which tile I fell into. I'm actually asking all the red points, whom among you is my nearest neighbor? Who is the closest to me? If you are the closest to me, I belong to your tile, and that's it. Okay? And so this is exactly what is known as the vector quantization, or in fact, the k-means algorithm in clustering. This is what people do. Okay, so here is a way of doing the very same thing without SK. Yes?
Can you repeat why you're using 2 to the power of b6?
Okay, suppose that I give you 4 bits. And with 4 bits, you're supposed to compress your image. Then you will have 2 to the power 4. That means 16 regions that your image may fall into. And once you tell me which of the 16 you fell into with a code of 4 bits, I can tell you which it is. Is it clear?
Yes, yes.
Okay, so b bits describe the address to the power b entities, tiles. Okay, so look at the following expression. Now SKs vanish, and I end up with a simpler expression that says every x is attributed to its nearest neighbor, and the distance squared times p of x dx integral over all the images is the loss. And now the unknowns are only the center points, only the xk's. This is exactly what k-means does. This is exactly what we do when vector quantizing. This is the ultimate compression algorithm. In fact, if you put aside entropy coding, you cannot do better than that. Now, are practical compression algorithms working this way? Never. Never. Why? Why?
You don't have P of X.
We don't. Well, it's not the reason. We do have a proxy of P of X, which is many, many training images. So why are we avoiding this method, which looks so appealing? Why?
Hard to optimize.
Sorry, what? Say again. Don't hesitate, Khan.
I was asking if it may be hard to optimize because it's very non-continuous.
It is hard to optimize, and k-means is a nasty algorithm that cannot guarantee convergence, and there are all sorts of problems, and nevertheless, we do it. And yet, this is not how we compress images, and the reason is 2 to the power b. I mean, think about it. 1,000 bits per image, it's not even generous. We compress images with more bits. 2 to the power 1,000 means that you will have an impossible number of vectors, unknown vectors to find. How can you do that? So you have a curse of dimensionality that will kill you here. This is why compression algorithms break the image into patches and do all sorts of things to trick all in order to avoid the 2 to the power b. But honestly, this is the best you could do ever. Okay? And in the theme of what I'm trying to convey here, look at the star of the game here. It's P of X. It's P of X. Knowing it is creating the ability to compress ultimately. Okay? So knowing P can lead to better compression. We were asking, what can you do with knowledge of P of X? And we gave sequence of answers. Here is another thing you could do: dimensionality reduction or sampling. Suppose that you get an image X from this distribution and you want to reduce its dimensionality to a much lower dimension. So you apply some sort of, let's call it encoder, okay? This is how you are familiar with it. The encoder is parametric with parameters theta. And there will be a decoder that will take the low dimension vector and turn it up into the something that is trying to recover the image. And of course, the distance between the input and the output, you want to minimize it. Here it is. This is the expected error, input to output. Expected in the sense that you multiply the L2 error between input and output times the probability of X dx. And it will be minimizing with respect to the parameter of the reconstruction and the sampling. This is the classic autoencoder that I'm sure you have used. Okay, so here again, P of X is central. Without it, you cannot do anything. Good. Separation. Suppose that you have a mixture of two signals, X1 and X2. A mixture means you get their sum, their mixture. You know what? Someone add even noise to them, and you are trying now to break them apart. Now, X1 is coming from P1 distribution, X2 comes from the PDF P2. Can you separate the two? This is known as morphological component analysis. For example, in image processing 10 years ago, what people did is to take an image and break it into pure cartoon and texture. Why? Because sometimes there are great algorithms that are designed for cartoon, but are horrible for texture, and vice versa. So by separating the two, you can actually now do optimal treatment per each content. So how do you separate? Morphological component analysis says, here is what you're supposed to do. Find X1 that is the most probable, and find X2 that is the most probable with respect to its own probability, such that their sum is epsilon away from Y. This is map. It works amazingly well. In fact, this result comes from this machinery. So again, knowing of P1 and P2 suddenly enables us to do things. What else? Anomaly detection.
Okay.
Yes.
Is it proven that the previous method you showed now is the most optimal one, taking the difference here?
No, because you have to define optimality criteria in order to claim anything. What you see here is a classic map. And in fact, you could also come up with an MMSE alternative to it. And each of them will be best in its own language. So in terms of getting the top X1 and X2 with the probabilities, this is it. This is what you're looking at. Okay? And people have been playing with it 10 years ago with a lot of success. I'm moving on. So I started talking about anomaly detection. Someone gives you an image and tells you, is this image okay? You have a probability of many, many images. All of them are images of dogs. Someone gives you an image of a cat. Does this image belong to the distribution that you are looking at? By comparing this probability to a threshold, you can actually answer this question. Something similar to it can be done by finding regions that are anomaly within a larger image. Classification. You never think about classification in terms of knowing the distribution, but this is exactly what you do all the time. Suppose that I have many, many images of dogs and many, many images of cats, and I'm trying now to get a new image and tell you whether this is a dog or a cat. How do I do it? Forget about the deep learning approach with the training and all that. If you know P1 and P2, the probabilities of dogs and probabilities of cats, here is what you're supposed to do. You're supposed to compute the probability of the incoming image and check whether the probability of dogs is larger than probabilities of cats and assign proper probabilities, a proper classification. This is what you're supposed to do. And when you have a classifier by indirect way, this is what you essentially do. You can synthesize. If you have P of X, you can sample from it. We will talk a lot about it next week. Sample from it using GANs, using variational autoencoders, using normalizing flow, or using diffusion. You can sample an image that looks like this. We have seen it before. You can actually twist this image to have all sorts of styles, and it's all about P of X and whatever it goes through as you change the style. So you can do amazing things. So we asked, what can you do with P of X? And the answer is many, many things. Almost everything that we do in machine learning, in signal processing, in image processing, relies on knowledge of X, either directly or indirectly. Okay, so obviously the question is, who is P of X? If P of X is so important, how do you put your hands on it? So this is the next topic. In this course, we will focus on P of X that corresponds to images. But again, much of what will be said here applies to other sources with adjustments. Okay. In the coming 10 minutes, hopefully I will cover the next portion where I talk about the classics. So imagine researchers 50, 60 years ago asking exactly this question, who is P of X? And coming with all sorts of answers. And these answers kept improving over time and created an evolution of answers about the identity of P of X. You won't believe it, but these people kept guessing P of X. They were guessing it. It's strange to guess something. Let me show you just the first few steps in this guessing game. Here is an untold secret. If you look at the literature of image processing over decades, it is essentially the evolution of choices of P of X and how to use it. This is all the literature. People come up with an idea, here is P of X, and then everybody jumps and they say, okay, if this is P of X, I can denoise. And someone else says, I can deblur. And someone else says I can compress, etc. And then someone comes and says, no, forget about this previous choice. Here is a better choice. And the game goes going and going. Okay? And again, it applies to other fields as well. So here is the evolution as I see it. Remember, we are about to do something totally crazy. We are about to guess the probability density function of images. I mean, it sounds stupid. How do you guess such a thing? Here's what you are supposed to do. You are supposed to ask yourself, what images are behaved like? What do you expect images to be like? And one of the first things that people notice is spatial smoothness. That means if you show me a pixel in the image and I look at its neighbors tend to be very similar to it, okay? And this spatial smoothness is a property that good-looking images tend to comply with. So let's come up with a PDF, P of X, that will tell us that smooth images are more likely than other ones. This is exactly the line of thinking that brings us to the early attempts on the 70s. Okay, so images are more likely if they are smooth. How do you measure smoothness of an image? Here is what you're supposed to do. I think that some of you are familiar with the operator known as L, the Laplacian. The Laplacian is something very simple. You have an image of size 100 by 100. You take every pixel, and you subtract the value of this pixel from the average of its 4 neighbors, up, down, left, right. You take for each pixel the 4 neighbors. You do something on the borders that will enable you to do the same computation. So you subtract the average from the pixel, and if this difference is 0, it really means that the pixel is in harmony with its neighborhood. Okay? Now repeat, do it for all the pixels, sum the squares of everything, and you look at this expression, norm of Lx squared. If this is 0, you have a perfectly smooth image. In fact, it is a tilted plane. Okay? If it is small, it means that most of the image is smooth. If it is high, it means that your image is unlikely to be true because it's too aggressive. Okay? So this is what people believed. Exponent of minus constant times this expression. So more smoothness, more likely this image is to appear. Okay? Lovely. Great. In fact, you know what? Let's play a game. If this is my probability density function for images, I can plug it into what we have done before. I remind you that 20 minutes ago, something like that, we have shown that the map estimate for an inverse problem is the least squares with regularization. Remember? And now we have an explicit expression for P of X. We can actually take P of X from here and plug it here. Let's do that. So log of this removes the exponent, minus turns this into plus, and we end up with this expression. Now look at this. Classic Tikhonov regularization. You are searching for X such that when it is degraded, it is not far away from Y. And among all those X's, please bring me smooth X's. Give priority to smooth X's. Classic regularization. In fact, the minimizer of this is easily obtained because it's all L2. We can take a derivative and we end up with this closed form solution to it. This is well known. This is familiar as the Wiener filter. And it works horribly. It creates images that are unpleasant to look at. For people working in the 70s, it was enough. For us, it's totally ugly. Why, in your opinion, is it ugly? Why? Why?
Not all images are smooth.
Or, put more broadly, the guess of P of X is wrong. You are wrongly guessing P of X, and what do you expect? You get poor results. Okay? So let's keep guessing. So people moved on. And in parallel to this guess, people came up with another guess, a guess that came from the knowledge of transforms. Remember, in signal processing, transforms are very popular. It started with Fourier and then moved in images to DCT. 2D DCT. And so people notice that if you transform an image with DCT, you can expect most of the energy to concentrate in the low frequencies. So say so. Tell me that your image is concentrated in the low frequencies, which is, by the way, another way of saying the image is smooth. Low frequencies, smoothness. So this expression says the following: apply your transform, and then multiply by a diagonal matrix, lambda, such that lambda is very high for the frequencies where you do not expect energy, so you penalize for it. Okay? Looks entirely different, right, from the previous guess, but it's the same guess. By the way, this is the origin of JPEG. JPEG is all about breaking the image into DCT, into patches, applying DCT, and coding the leading coefficients. This is how compression with JPEG is working. Great. Now, this is a Gaussian. This is a Gaussian. So basically, people guessing this or this, we're guessing that images are distributed by a Gaussian law, which is not necessarily true. In fact, you can make the two equivalent if you choose this connection between lambda t and L, okay? So basically, people that suggested this didn't suggest something new. They suggested something different that is perfectly aligned with the previous guess. And so if this doesn't work, this will not work as well. And this brings up the question, if this is so horrible, and this is the origin of JPEG, how come JPEG works so well? How come we are still stuck with JPEG? Any idea?
Maybe patch-wise, it's more correct than image-wise.
Excellent answer. This is one answer, and there is more to it. If you look delicately into the JPEG design, here is what's happening there. You will be prioritizing the low frequencies, but if there is suddenly a coefficient with large energy in the high frequencies, you're not going to wipe it. You're going to allocate bit to it. It will cost you bit. And so you are not just believing that it is low frequencies, you are also serving high frequencies when they exist, which is of different flavor. This is why JPEG is still vivid, even though these attempts from the 70s are long dead. We have one more minute, so maybe I'll say one more thing and then I'll stop. Another group of people did something far smarter than that. And they said, you know what? If we believe that images are Gaussian, let's fit a Gaussian. This is leading to the KLT or the PCA. You know, you give me many, many images, vectors in high dimensional space. They are supposed to organize themselves as a Gaussian. I can actually estimate the Gaussian, estimate the mean, estimate the covariance, and come up with a Gaussian. People did that. But it's still a Gaussian. So if the images that we have are not Gaussian distribution, all three are actually poor options. The elegance about the green option here is that it is learning, at least it is adapting. It's not guessing something like the Laplacian here or the transform here, but still Gaussian. And then came the 80s, and everything else that happened will be explained next week. So we stop now. Questions? Remember, all this is background. Slowly and gradually we'll get closer and closer to diffusion, and everything that I'm describing here will become the obsolete story. Questions? Okay, I'm stopping the recording.